it's my great pleasure to welcome back Ben. Very few of you, maybe only Ed, were around in 2006, 2007 when he graduated as an undergraduate here. Since then, he's been a PhD student at Berkeley. He's worked at Twitter. He's now co-founder of Mesos, a company which, as he'll probably explain, helps provide enterprise solutions on top of Mesos. And I thought I would do the, all the normal cheesy introduction stuff, but then I had a much better idea to go back and try to find the first email Ben ever sent me. So spring of 2004, I taught my first undergrad class here. It was CSE 341, and I hadn't yet figured out how to collect survey results using the internet other than using email. So I made everyone email me a little beginning of class, like, who are you? And it's not very exciting, except what is something about you I probably would never know without reading the answer to this question. And he wrote, I love to ski as much as I love computer science. So it's nice to see that as much as Ben has changed in so many ways in 12 years, that is not one of them. Ridiculous.
Awesome, fantastic. Yeah, thanks so much for having me. It's great to be back up in Seattle. I love coming up here. It's a gorgeous day. I know the weather is always like this the whole year. So I thought when I was thinking about the kind of presentation I might give here, I would give it's kind of different ways you can think about this presentation. One way is this is sort of the work that I did in grad school. And it's both the work that I did pre a project that I now spend most of my time working on called Mesos. And then the other way to kind of think about it is it's really the talk is really motivating why Mesos was built the way it was built, and then also discussing a little bit about how Mesos is being used now by the company that we created called Mesos here. So hopefully you enjoy it. Schedule activations is in this talk, so it's great to see Tom and Ed. So usually when I talk about that part of it, I just say whatever I want, and that's what schedule activations are. But this time maybe I'll get some great criticism. That works for us. So I'm going to jump in. So I'm going to kind of start this off by giving a little picture to again motivate Mesos, but then there's kind of a talk within a talk. Distributed systems are really hard to build. There's lots of presentations out there where that's where the presentation starts. Like, oh, distributed systems are super hard to build. How can we make it easier to build? What are programming language techniques? What are system techniques? Yada yada. One of the things that was really interesting for us with Mesos was, in some ways, we were less interested about making distributed systems easier to build, and actually we were even more interested in making them easier to run. Because as hard as distributed systems are to actually build, I would argue that in many ways they're even harder to operate. They're even harder for people that get these things and try to go run them in their production environments to be able to operate, to deploy, to maintain, to update. There's so many distributed systems that exist in a lot of people's organizations that never are ever upgraded because it's just impossible to do, so they're going to run the old version forever. They're so hard to actually operate that there's a whole book industry that creates books for every distributed system that gets built. When you want to go operate that, you have to go buy the book for running Hadoop or the book for running MySQL. And this to me is this is the really fun way that a lot of people actually operate distributed systems. They start with, like, okay, I want to run that distributed system. They go ahead and they download it. Then they're like, all right, well, I want to deploy the distributed system, so what's the best way to deploy it? Is there certain high availability strategies I want to use? Do I need to think about network latency? What do I want to do? So they read the book, they figure that out, then they deploy it. Now it's up and running, and they're like, well, I should probably know something about the system, so perhaps I'll monitor it. So they start to learn how they can actually monitor the system to see what happens when things fail. Again, they might go back to the book to figure that out. And then comes the fun part. And they actually want to maintain their distributed system up and running. So when something happens, when a crash happens at 2 a.m., and something goes down, and their great monitoring system actually noticed it, they're like, crap, what do I do to fix this? So, they go on IRC, they try and get in touch with the person that actually built the system. Whatever they do, they try and fix it, and they fix it. And then about 2 weeks later, the same crash happens, and they're like, oh, what did I do again? Crap. They look through their history, they try to find it, and they say, that's what I did, and they write that down. Because they're like, I'm never going to have to do this again, and they write that thing down, right? And then 2 weeks later, when the same crash happens again, they're like, you know what? It's super easy to detect when this crash happens. I do exactly this thing, so I'm just going to write a script, which is going to do exactly that. So then they write the script, they're like, this is better, okay? And then eventually the script gets so complicated that the next thing you know, they've built a whole separate system to actually operate and monitor the first distributed system that's set up. And then this process just kind of continues to cycle. And then it gets even tougher once they've done all this maintenance stuff and they actually think about how they want to upgrade or redeploy or whatever. And so there was this perspective that we really had. One way that we really thought about what we were trying to do when we were first building Mesos was, couldn't we make it so that distributed systems could actually operate themselves? They could deploy themselves, they could monitor themselves, they could update themselves, they could upgrade themselves. And I think a really key thing that we said was to enable a system to be able to do something like that in a data center, in the cloud, in a cluster, whatever it is, we really needed to have some kind of a software interface so that the distributed system could communicate with the underlying infrastructure to be able to do what it is it might need to do to operate itself. And that kind of in a crux is what we were trying to build with Apache Mesos. So there's a couple bigger picture slides that I'll talk through, and I'll relate them to other things. But the reason why you really want the distributed systems themselves to do this, to be in charge of operating themselves, running themselves, scheduling tasks themselves, everything, is because humans really have inadequate knowledge of the distributed systems needs. They can't make the most optimal decisions, even after reading the book. They still can't make the most optimal decisions for the distributed systems. And really, before we started doing some of the Mesos work, distributed systems executions, needs, or statistics can't easily or efficiently be expressed to the underlying infrastructure. There's either too many different kinds of underlying infrastructure, or it's just too hard to actually express it. So I'll kind of come back to this. It's a theme throughout the rest of the talk. So maybe you can see some of the schedule activation stuff sneaking through. We'll get there. Just a few more thoughts about when I say operate, applications operate themselves. This is really what I mean. On Linux, applications, for the most part, they operate themselves. On Linux, when an application needs more CPU, it says to the kernel, hey, I would like, in this case, more threads. We might want to argue that the better abstraction would be, I actually want another CPU. I don't want a thread, or I don't want a process. I actually want the CPU. But they have a way of, when they want to do more things, they can just say to the operating system, I need more threads. When they want to do things like reads and writes, they can say, hey, I want this. I want to perform that function. And that's what I mean when we really capture, when Mesos, when we say distributed systems operate themselves, we mean when they want more CPU, they can just ask something for that CPU. When they want to perform a function like creating a persistent volume or doing whatever they might want to do in the data center, they can just actually ask to actually do those things. And so there's this interface. Back to what I was talking about earlier. On Linux, there's this interface between the operating system, the kernel, and the applications that are actually running so they can operate themselves. And we really want to provide that same interface, and that's what we did with Mesos, so that the distributed systems can, again, operate themselves. And of course, Mesos sits across many machines, and Linux, it's just across one machine. Sometimes I forget why I have things on my slide, and that was that was why. Okay, so now, with that kind of hopefully motivation, I'm going to take the talk in a totally different direction, and I'm going to dig in for a little about, when I say, when they operate themselves, when they need more CPUs, they ask the Linux kernel for more CPUs. I'm really going to kind of dive into what I mean when I say how applications get CPUs. Because the way in which we do this in Mesos, and one of the reasons why Mesos ended up being interesting from that perspective, is very, very much based off of existing research that people had done on single host operating systems for doing scheduling, because really getting more CPUs is scheduling. Right? Asking for more CPUs is because I need these things so I can actually run my jobs. And so this mini talk within a talk is the case for multi-level CPU thread scheduling. The greater talk was the case for multi-level scheduling, and this is kind of the case for multi-level CPU thread scheduling, and why, if we want it there, why wouldn't we also want it in the distributed systems? Okay, this is where we start to get to the schedule activations fun stuff. Okay, so before threads, there was fork. If you wanted to get more resources, you had to fork. Okay? And then you had multiple processes, multiple user space processes. So what I'm identifying here is there's a kernel space, there's a user space. If you want to do things in parallel, you had to fork, get more processes, run those processes. Okay? There's only one scheduler in this system. It's the kernel level scheduler that's mapping these user space processes to the underlying CPUs. Okay? Now we introduced user level threading. That was one of the first things we introduced, because you could do a lot more interesting things in the user level space. Okay? Now now we had what we commonly refer to as the N-on-1 model. We had n user-level threads that somehow got mapped to a single kernel thread. And you only run one of those user-level threads at a time, and they call into the kernel. Okay? And there's a bunch of advantages to this model. One is really fast context switch times between the user-level threads. I have to go through the kernel. I could just switch my registers, run the other thread, super fast, everything's great. Really fast user space synchronization primitives. Again, didn't have to go through the kernel to do synchronization really fast. But the biggest crux here was the unnecessary blocking. Especially on I/O, when a user-level thread went into the kernel to do some I/O, you blocked that entire process being able to do anything, even though those other threads could potentially do some work. Right? Okay? So eventually, what we've really evolved to in our industry is one-on-one threading, where there's a single user-level thread that effectively maps to a single kernel thread, and the kernel just schedules each one of those user-level threads. So now, when a user-level thread goes into the kernel to block, it just blocks that one kernel thread, and all the other user-level threads are free to execute on their own. Of course, the downside now is we've got extremely expensive context switches, because to swap between the threads, we actually need to go into the kernel, grab another thread, and there's still some of the issues around synchronization primitives in user space. I mean, I'm not going to kind of go into more details, but we've spent a ton of time in the industry dealing with these synchronization primitives, and ultimately we've gotten to effectively as hybrid model of user space, kernel space synchronization called Linux Futexes, which is pretty much what we do to avoid a bunch of the problems. So there was a question that I'm sure some folks were asking themselves. This is totally my take on schedule activations. But there's a question which is, could we get n-on-1 plus 1-on-1, the best of both worlds? Could we get n-on-1 fast context switches? Could we get fast user space synchronization and no unnecessary blocking? And there was a technique that could do that really effectively using this idea of schedule activations. And the idea here is we'd have n-on-m threading. Okay? And so what we do is we'd say, all right, there's n user-level threads that are mapped to some number m kernel-level threads. And now there'll still be a user space scheduler that's trying to decide what are the best user-level threads that it can actually map to the available kernel threads that have been allocated to it. And to me, I mean, the real power in scheduler activations is saying that the kernel-level scheduler wants to be able to communicate with user space via these upcalls, via these events. We can start to do really interesting thing with user space. And this is kind of the crux of the next work I'm going to talk about, some work that I did called Lithe, and then the Mesos work as well. And in this case, the upcalls from schedule activations were things like a virtual processor has been allocated or deallocated from you, or this activation has blocked or unblocked, for example, due to I/O. Right? So we've introduced a direction of communication in the operating system that previously we didn't have, which was the kernel actually being able to call back up into the user space when really there's only user space calling back. Now, why did we do this? Well, again, my take is it's because the kernel-level scheduler had inadequate knowledge of the application's execution needs or semantics to make the most optimal decisions about what you might want to schedule next. The user-level scheduler was far better at doing those things. And the user-level scheduler couldn't easily or efficiently express that down to the kernel-level scheduler. So we introduced an interface to let these two things communicate more effectively. And an even bigger picture than that, which is mechanisms that facilitate the exchange of information between levels of abstraction is a good thing. Like, we still want levels of abstraction. That's really important. Abstractions exist for a good reason, but without sufficient communication, they really force suboptimal outcomes. And the other example that I love to pick on from the operating system space is the LRU page replacement. The LRU page replacement algorithm. Least recently used, works great for all those applications except the application that is about to touch the page of memory that it least recently used. Right? So fantastic. What if instead the operating system could just say to the application, I need a page back, tell me which one it is. And we have this communication in both directions, so you can do things faster, right? Like, without sufficient communication, they force suboptimal outcomes. The LRU forces a suboptimal outcome because there's not communication there. Okay, so just a really funny tidbit, because NMM to me was like, right, when I first read about it. And so where is it today? I mean, Linux is just one-on-one. NNM existed in NetBSD and FreeBSD for a really long time. They've also abandoned it for one-on-one. But the whole concept of multi-level scheduling still exists today, right? And the next part of my talk is going to be all about this because that's where I started my research career. I started my research career here, but that's where I started my research career at Berkeley. Yeah.
So just an observation that it's actually in Windows.
So, come on, let me get to that slide.
Oh, okay. Sorry, I didn't realize. I thought you were going to go on.
Yeah, no. So I mean, multi-level scheduling exists today. If you take something like Intel's threading building blocks, where they're trying to decide the best way to schedule the tasks in their DAG, they're trying to do that, but they don't have the mechanisms like NNM to do that really, really effectively. And so they're basically doing NNM scheduling today, but without any of the primitives that you would have gotten from something like schedule activations. And the one place that it does exist today is Windows 7 and on, where they didn't introduce this upcall mechanism, but to the best of my knowledge, just for blocking and unblocking, not for also being, to allocate you more kernel threads, if you will, or CPUs, or so. I mean, it's great that it has at least some of that, but not all of it. So today's reality, which I think is really fascinating, is that it's much, much worse than NNM. It's NNM compounded with P on Q compounded with RNS. And that a lot of applications that run today are really doing this deep nested intra-process multi-level scheduling. And so I'm going to spend a little bit of time talking about that because that again motivates where the Mesos project really came from, and it was my previous research. So the example for this intra-process multi-level scheduling is sparse QR factorization. So the way the algorithm works is first you run a bunch of tasks in parallel. These tasks are doing a bunch of work. Each one of these tasks calls into the MKL, the Intel Math Kernel Library, for doing some basic linear algebra. Each of the MKL calls themselves have a bunch of threads, and so this just kind of expands like this. Okay? And so effectively what's happening is that we're doing everything that we were taught in computer science, which is we have this functional composition of libraries. I call into one library, that library calls into another library, and they're all just doing whatever they want to do with their resources, and everything works and makes sense, right? So in this application's case, we use Intel's threading building blocks, and as I already mentioned, in this application's case, we're using MKL. But specifically in MKL, we're using the OpenMP programming library. And so there's this question that comes up when you try to run an application like this, which is, what's the best way to actually allocate resources between these different libraries, between these different instances of stuff that's running at the same time? Right? If I have a 6-core machine, is the best thing to do to give TBB 3 cores and OpenMP 3 cores? Is the best thing to just let them create any arbitrary threads, however they actually want to create them? And one of the real tricky questions that we started to realize as people were building more and more applications that look like this is you really wanted to be careful to not overcommit resources, because the possibility of overcommitting resources could cause really, really bad performance effects. Okay? So to understand what might be the best way to actually allocate these resources, let's just dive in a little bit and look at what the SPQR software architecture looks like. There's a system stack, hardware operating system. There's the SPQR application. It uses some part of TBB. What TBB is doing is creating what they call the column elimination tree, which is a DAG of tasks that have to get executed. And within the DAG, within each of the executions, we're doing frontal matrix factorization. I actually don't know what these words mean, but that's what SPQR does. The crux of this DAG when it ends up looking like this is that the leaves, we're doing a lot of computations simultaneously, and we really want to be careful that we don't overcommit here, because each TBB task is creating M threads per MKL instance. Okay? And you can get pretty horrible performance. In fact, you can get such bad performance that if you go and you get Intel's MKL documentation, and you read about how you should use MKL with something like any other parallel library, like TBB, they say, if more than one thread calls MKL and the function being called itself is threaded, it is important that threading in MKL be turned off. So you'll get such bad performance from overcommitting resources that don't even bother using this library in a parallel way. Just do it completely sequentially, right? In fact, that's the old one. That's the older version. This is the more recent version of the doc. I looked it up last fall when I gave a little bit of a variant of presentation similar to this to see if it had changed. And the docs had changed a little bit. Now what they say is they say, choose N carefully. Which is like so wonderful, right? And then I love this. It's like example 1, if application has 2 threads and each thread calls MKL and the system has 8 core, it's reasonable to set the number of threads to 4. Because 4 times 2 is 8, and therefore you're probably going to be using all the resources. Like, this is the state of the art still today in composing parallel libraries together, which is what every single software engineer is learning in their undergraduate software courses. Is I'm just going to call this library because functional abstraction is going to do what it needs to do. And then later, when they have horrible performance, they realize maybe I don't want to do it that way. So the recommendation fundamentally in parallel programming still today is static partitioning. Statically partition the resources you're going to give to each of the libraries, or at least the threads in this case that they're going to create to actually run the application. So fix the number of CPUs or threads between each one. So in this case, we had 2 and 4. Or maybe it was 4 and 2. I forget, whatever it was, but it's 2 and 4, okay? And we have to ask ourselves, is this really the optimal allocation? Is this the best way to do it? So if you go back to Intel and you ask them, well, what do you recommend to do based, if this really is this really the optimal allocation? Is 2 and 4, or is it 5 and 2? That doesn't equal 8. 5 and 3. You start asking what is actually the best optimal allocation. The next thing they say is well, try manual tuning, because every application is a little different, and so you might want to try all permutations of thread applications. So it's static partition, but it's even worse. So this is actually a graph of this the SPQR application. It's showing giving the number of threads to TBB versus the number of threads to OpenMP, and all the different performance pieces that you get there. And what you notice is that kind of default out of the box with static partitioning, when you start doing this manual tuning, you can really start to get quite a bit better performance. Just by doing the manual tuning, trying all instances, you can get the performance. And really the question that we asked at Berkeley is we said, can we do even better than this? Because manual tuning, why do we want to do manual tuning? Is there anything that we can do that would be even better than this? Oh, you guys couldn't see that slide yet, sorry. So we asked, can you do anything better than this? And what we recognize is that most applications are dynamic. They're inherently dynamic. And the downfall of picking a static allocation, even if you manually tune, is that in certain parts of running the application, the best allocation is X. And at other parts of running the application, the best allocation is Y. And so the SPQR graph really looks something more like this, where at the top of the graph, if you could give all the resources to MKL, you should, because TBB is actually not doing anything in parallel. So why not give more threads to OpenMP at the beginning, and then later down, when you're trying to run more TBB tasks in parallel, then you give less resources to OpenMP. And again, the message here is that static partitioning is a kind of scheduling, and it's suboptimal. because the scheduler, the human, is missing information, right? So getting back to, again, we're missing information to be able to make the most optimal decisions. And so what we actually built at Berkeley was a project called Live, and it was multi-level scheduling between libraries. It was this idea of introducing this interface, just like scheduler activations introduce an interface between the kernel and the user space. Can we even just introduce an interface between user-level libraries themselves? Keep everything in user space and still introduce that interface. And so the basic idea is, dynamically allocate CPUs and threads between TBB and OpenMP in the same way that you would N on M dynamically allocate resources between the kernel and the application. And do that specifically so you can match the demand as closely as possible. And we were really lucky. Like, we just did this, and without having to really do much, we'd just run it, and it would, in all circumstances, run better than manually tuning, because we would be able to take advantage of those spots where you'd really want to give the resources much, much differently than in other places. So this is us actually running with Live. Now, there's a bigger picture message here, which I actually found to be the most interesting coming out of this work, which was less about the multi-level scheduling within a single application. It was more about this idea that I've kind of alluded to earlier, that we're so ingrained in this synchronous functional programming model about this idea of explicitly transferring control. When one library calls into another library, you explicitly transfer control. But we never think about the fact that you're implicitly transferring resources. And when you call into some other library, you're effectively saying to that library, here you go, here's my CPU. If I've just read a bunch of stuff in from disk and it's all in the cache, here's my cache. You might completely muck with my cache and kick everything out. And when I go to run again, I'm going to have bad performance. And we don't think about the fact that we're actually giving our resources to whatever we're calling to. We're just giving our control. And so what we said with Lies was we said, well, let's try to make, at least for the extra resources, maybe not for the very first call, but for all the extra resources that we want to give you, let's make that explicit transfer of resources happen instead of everything implicitly. Okay, so Lithe to Mesos. So Lithe was about sharing a machine's resources between libraries within a process via multi-level scheduling. And this really evolved into thinking, how could we do some of this similar multi-level scheduling work in the data center as well? And the reason why this really happened is because some folks in the distributed systems lab came up to me and they said, hey, static partitioning is the way that we run our distributed systems. We take a couple machines and we say, these are the machines that we're going to run for this distributed system. And we take a couple other ones and we say, these are the machines we're going to run for these distributed systems. And I said, oh, well, why don't you run some distributed systems on the same machines? And they said, because when we did that, we overcommitted resources and everything was horrible. And I said, that sounds really interesting. I wonder if we can do something really similar to what we did before. And so we had this idea that static partitioning in the data center was probably not a good idea for the same reason that static partitioning of just cores and threads is not a great idea. And the canonical example of static partitioning in industry today is you take your front-end applications, your Rails applications, you take your analytics application, something like Hadoop, and then maybe you take something like your database, or in this case I picked Memcache, and you statically partition it up. And the resources that are actually being consumed by these applications vary dramatically. And you don't end up being able to take advantage and run everything as efficiently as you possibly could because you've done the static partitioning. So in the same way with a thread, you couldn't let the OpenMP at the top of the SPQR graph use more resources. We can't let Hadoop scale up and use more resources because we statically partitioned it into a smaller group of resources. But if instead we could have this model where we could really dynamically move the resources between the different applications much more dynamically, then we could scale up and we could run things faster, and we can of course drive up our utilization in our cluster, which means effectively things would cost less. Okay, and so in the parallel programming world, one of the things we didn't care too much about was failures. But in the distributed systems world, the other place where static partitioning was really hurting organizations was when they just happened to unfortunately do the scheduling where the static partition was a bad one. The scheduling was a bad one, and you'd lose resources that were specifically statically partitioned for one particular app, and then that app wouldn't be able to run. And I'm going to talk about that a little bit later when I talk about how we use some of the stuff at Twitter. And so there's this idea like, what if we built something to manage resources in the data center like Lithe manages resources on a machine, or we built something to manage resources in the data center like Schedule Activations manages resources on a machine. And that's where really Apache Mesos came out of. It's a cluster manager based on these ideas of multi-level scheduling. And so again, getting back to some of my very beginning slides, Mesos make it easier to build and operate distributed systems by providing an interface, this upcall interface between the infrastructure underneath and the distributed systems that are running themselves. Okay, so this goes till 420. 420, 430. Okay, so I have too many slides. So I'm going to talk a little bit about Mesos and kind of the background about Mesos and kind of give you a bit more details of what it's all about. And then I'm going to transition at the end a little bit to sort of what we're doing with it today in industry. So Mesos is a cluster manager. It has a master agent architecture. There's a bunch of masters. They manage a bunch of machines, a bunch of agents. And really what we did was we challenged the status quo of cluster managers. The status quo of not using cluster managers was static partitioning. But there were still some people out there that were starting to use things like cluster managers to actually run their applications. Less so for the kinds of applications we were interested in running, which was big data alongside stateless microservices, request response services, databases, distributed file systems. And that's really the way we were thinking about how we'd want to run our cluster managers. And so most of the cluster managers that existed in the past, the status quo was this idea that an application or a human, when they wanted to run something on the cluster manager, they'd submit what they call a specification, which would effectively describe the job they're trying to run. So you would show up and you say, I want to run this job. You'd write out the specification, you'd submit the specification, and then it would run on the grid, right? The cluster manager would actually run it. And what was really interesting about this model is that after you'd submit this, then you'd have to wait. The application would wait. The human would wait. You basically have to wait until the job actually ran. And then finally, the result would come in. And what we noticed was really interesting is that a lot of times what would happen is a human would submit their specification, and then they'd go look and they'd see where it is in the queue, and they'd be like, darn. I wonder why it's there in the queue. I wonder why my job's not going to run earlier. And then they kind of look at maybe what else is running in the cluster, and they'd say, you know what, I think if I resubmit my specification with 5 less CPUs, my job will run right away, because it'll fit in this area where it's using less resources. So sure, why not? I'll do that. So you had these humans that basically couldn't express exactly the way they'd want to run their applications, and they would game the system by scheduling, by being their own scheduler. So that was kind of the first part we realized that specifications were hard. It was hard to specify certain desires or constraints, like I'm submitting for 8, but I could run with 5. Only if the 5 looked kind of like this part of the 8, whatever it is, right? But then the other one that we realized was much more interesting was for a lot of the kinds of distributed systems we were thinking about running, it was really hard to be able to change these specifications dynamically. And I'm going to talk about this second one in a bit more detail with respect to MapReduce. But first, again, it was this bigger picture of the cluster manager has inadequate knowledge of the distributed system's execution needs or semantics, and the distributed system's execution needs or semantics can't easily or efficiently be expressed to the cluster manager. So in the MapReduce case, it was especially interesting because MapReduce is a pretty complicated beast. A distributed system that goes through a couple different phases, map and reduce, including a shuffle phase, a sort phase. And what's really interesting about the way in which you might want to run something like MapReduce on a cluster manager is when you try to think about the specification of the amount of resources that you need to something like MapReduce, you have to ask yourself a question. Do you want to make that specification be a really fine-grained thing? Or do you really want to make it be a coarse-grained thing? Or can you even do that? And the reason I say that is because if you could do it in a fine-grained way, like you could literally have the specification be for every single map task and every single reduce task that you're trying to run, then that's fantastic. Because then the cluster manager can know exactly which jobs you're trying to run, exactly the amount of resources you're trying to do, and just do it. Whereas in a coarse-grained way, where you just say, oh, give me 400 blobs, and I'll just use those 400 blobs across my entire MapReduce thing, you're not going to get the best resource utilization, but it's going to be really, really easy to specify that to a cluster manager. And in MapReduce's case, in Hadoop's case, what's really interesting about it is the resources that you need in the map phase versus the resources that you need in the reduce phase are very, very different. It's very common that in a MapReduce job, you'll run like 10,000 maps and 5 reduces. You're a lot more maps, and even specifying that in a fine-grained way is still a hard thing to do because it's not as simple as, okay, telling the cluster manager I need 10,000 and I need 5, because it's 10,000 and then my 5, but maybe some of the 10,000, the machines died, so I got to respawn a couple of these other ones to run this, and all of a sudden we're getting in the business of Hadoop, the logic of how it actually works or how MapReduce actually works, and how can we really efficiently express all this in a fine-grained way to a cluster manager. And so we said, all right, well, we can't. Instead, why don't we just say, why don't we have something like a Hadoop register with this other thing, with what we called Mesos, and say, we'll do something where we can more effectively and efficiently let Hadoop specify the resources that are required dynamically over time and do effectively multi-level scheduling. So in the Mesos model, what happens is these things that want to run tasks, these distributed systems, they register with Mesos, and then we go through this little dance. And the way that works is when one of these things wants to actually run an application, you submit a request. So just like the application or the human in previous cluster managers would submit a request, you'd still do that here. And I'm calling this the coordinator because this is kind of, you can think of it as the coordinator of the distributed system. We call it the scheduler in the actual code base because it's scheduling and it relates much more closely to the live work that I previously talked about, or user level schedulers and scheduler activations. But this thing does, when it wants to actually run some resources, it submits a request, and then we had to ask ourselves the question in Mesos, well, what should we do if we can't satisfy that request? You know, request comes in, we can't actually satisfy that request. In an existing cluster manager situation, we just wait, right? We just say, great, we got the request, when we can satisfy those resources, we'll actually wait. But what we did instead is we said, well, why don't we just offer you the best allocation of resources we can make at this point in time. And let the software figure it out, or let the human figure it out. But let the software decide if maybe there's a better thing that it can do based on what resources are actually available for it to run its job. And so that's the one we picked. Okay? And so now, you know, the way this works is requests will come in, but then Mesos itself will say, okay, here's the resources I can offer you to run your jobs based on the request that you can actually made. There are many offers. And then the distributed systems themselves decide what resources they want to use to actually run those tasks.
Why are there many offers?
Because things are coming and going, machines are failing, many offers over time. Yep. And this really is an instance of multi-level scheduling. So first level, sorry, let me get to the next slide. So first level, Mesos saying, we'll make allocations to you via offers, and then the second level, the distributed system saying, via these offers, via these allocations, we'll decide which tasks we actually want to run these tasks using these offers. And again, getting back to this idea of scheduler activation, what was introduced here in scheduler activations was this upcall ability for the kernel level scheduler to communicate with user level. And what we did with Mesos was we said, let's create this communication interface where the first level scheduler in Mesos, what we call the allocator, communicates with the underlying distributed systems with these upcalls or these events. So you know, these are very similar to the interface in scheduler activations. Resources have been allocated or deallocated from you. That's the kernel level threads being allocated or deallocated. Tasks that you've been running have completed or been preempted or anything else. And really what we're doing here is we're introducing a level of abstraction. I think you or you, one of you said you solve all problems in computer science with a level of abstraction, and so that's what we're doing here. A level of indirection, that was the quote. You solve all problems in computer science with a level of indirection, and that's effectively what we're doing here. We're introducing a level of indirection. The coordinators speak directly through Mesos versus just being allocated a static set of machines. And then that lets us start to do really smart things about allocation and deallocation of resources. And that lets us start to do things like this, where you know blue is for coordinator 1 and red is for coordinator 2, and we can bounce back and forth the resources and change the allocations much more dynamically, matching demand as closely as possible with the resources that are actually available. Okay, now what was really interesting is this thing started, you know, Mesos really just started thinking specifically about the scheduling aspect of the things that it could provide in this two-level model. But where we really got to is we realized it could do a lot more. As long as everybody was communicating with Mesos directly, we didn't just have to think about resource allocation and deallocation. We could start to do a lot more really interesting things to make it much, much easier for these distributed systems to actually run themselves. And so kind of bringing the conversation back to where I started the talk, we started to realize that we could start to introduce a whole bunch of primitives that ultimately would make the distributed systems themselves be easier to operate. And so this is just a list of them, and this list just keeps growing every single day. When someone says, oh, we ran this distributed system in this way, and it would be great if you could help us do that, we say, that's a primitive we can go build into Mesos that distributed systems could actually take advantage of. Okay, so so I'll talk really briefly about, you know, when I was talking about the two-level model of Mesos. Yep.
So you have coordinators. Do you have one coordinator per job, per batch job, or how does coordinator correspond to the jobs that you actually have?
It completely depends on how you're trying to build your distributed system. You could have a scheduler per batch job, or you could have a scheduler for a collection of batch jobs. So for example, with Spark, it's a scheduler per batch job. For Hadoop, it's one scheduler for all the jobs that are submitted to Hadoop. Okay, so the first level algorithm that we actually built into Mesos was kind of interesting, so I thought I'd just spend a couple of slides on it. It was a fair sharing algorithm that we called dominant resource fairness. And really what was fascinating for us is we were coming out of this whole static partitioning world, and we wanted to solve this problem of if we were to bring the data center all together, if we weren't going to have it be statically partitioned up to a bunch of different organizations, what would we need to do from a first level allocation perspective to convince everybody to pool all their resources together? Right, so again, in most organizations, you had the static partitioning, and what we wanted to say was don't do the static partitioning, actually pool the resources into one big collection of resources, and trust us, you'll still get as many resources when you're one big pool as when you were separate. So that's a problem statement. Everyone understand the goal we're trying to get there? In this case, when this stuff is split out, it's fairly shared, but in certain circumstances, it might not be exactly fairly shared. Promotions might only have a couple of the resources. Trends might have a lot more. Recommendations might have more, whatever it is. So the goal is to fairly share the resources without static partitioning. And what we recognized, which was really interesting, is in the static partitions, you would run out of one resource first. If you looked at the utilizations in each of the partitions, at some point in time, you couldn't launch another task. You couldn't launch another service, whatever it is, because you ran out of resources. So this observation that we had was that there was a dominant resource for each of the partitions that basically bottlenecked every team from being able to do anything else. Okay? And when you looked at this case, for promotions, they bottlenecked on RAM first. For trends, they bottlenecked on RAM, but in recommendations case, they actually bottlenecked on CPU. And so there was this insight that said, could we devise a fair sharing scheduling algorithm where each team or each previous partition, we would guarantee that they could run at least as many jobs by doing a fair share of their dominant resource. Okay, so I actually, this is the way we write it in the paper, but the way I like to explain it is a little bit more like this. I like to personalize it, be like the person that's like, I gotta make sure I get at least that much memory in my machine. And so, the way you can think about it is that if my team gets at least 1/n, where n is the number of partitions, of my dominant resource, I'll do no worse than if I had my own cluster. But now I might actually do better, because by adding more resources to the cluster, I might be able to run another task. Because by pulling in those things, there could be spots that in other people's partitions, they previously might not have been able to run things, where I can now run things. So that was really nifty. That's DRF. That's still today the first level algorithm in Mesos. It's far more complicated than that. It's weighted DRF. It has got reservations and quota and a whole bunch of other stuff that we've actually had to build to make this be something that you can use in a production grade. But it worked. And here's just a quick snippet of showing at one point in time you're running a couple different analytics workloads, and you can let one job really scale up and use a bunch of other resources. But when more people are trying to run, you can kind of see there's 4 blocks there, and everyone's getting their 1/n of the share of CPU for actually running.
Do you have to assume that the different users are cooperative? Because how do you prevent the problem where?
That's a deeper question that I won't get into right now. So we continue to do some really, actually I've got some slides at the end of the talk where I can start to talk about some of the new things that we're doing in Mesos to specifically deal with cooperative versus non-cooperative schedulers. In fact, maybe come grab me afterwards, especially because it's 4:17 and I want to wrap up. I got a couple more slides I want to get to. So there's a lot more to Mesos that I'm not talking about, like cooperation versus non-cooperative. I just kind of wanted to hit the high-level points of really capturing this idea of multi-level scheduling and how it kind of permeates through all these different places. We've been really fortunate, and Mesos itself has been a piece of technology that's been used in production at a whole bunch of places. I just listed some of the organizations that I've personally worked with and to actually get this technology to deploy. And we've been more fortunate in the sense that cluster management has really surged in interest in the last couple years. And so I kind of wanted to spend a little bit of slides talking about that and then kind of wrap up with how we're doing this at Mesosphere. To me, one of the big reasons why cluster management has really surged is because in industry, there's a lot more organizations that are basically writing what looks like service-oriented architecture all over again, except we're calling it microservices. And they're containerizing everything. So applications are becoming even easier to schedule in these little units. And both of those things are really leading to this idea of why not have something like a cluster manager run these things for you in the data center on the cloud. I personally like this version of this slide because there's a lot of people that are doing microservices that are not doing containerization, but they still get into cluster management. In fact, a lot of people that do microservices and cluster management eventually do containerization. There's some people that are doing containerization and cluster management, and they eventually start doing microservices, and they get on this like trend, and then they're doing all the things eventually. And then there's another big one that they're also doing, which is big data and analytics. And in the same way that they're starting to think about what's the best way to run their microservices and run their containerization, they're asking what's the best way to actually run their big data and analytics. At Twitter, the reason why the Mesos project was successful at Twitter is exactly the microservices story. When I first got to Twitter, Twitter was a giant monolithic Ruby on Rails application that we called the monorail. Go Seattle, good name. And basically what we did was we decomposed this giant application into a whole bunch of services. And you can go back and you can look at talks from 2010 from Twitter where they said we were moving to a service-oriented architecture because no one was calling it really microservices yet. But that's what we were doing. We were breaking up our applications into a whole bunch of these microservices. And for the ops team, the move from this to this was like super scary, right? Because the ops team used to say, I know how to deploy one thing. It's super easy. I've got this one binary I deploy on thousands of machines. It's great. And now all of a sudden we said to the ops team, oh, now we're going to deploy tens of these things. And it wasn't just tens. It went from tens to 20s to 30s to 50s. And Mesos really got introduced to Twitter because people realized there was a need for this new infrastructure. Microservices and containers and big data and analytics and all these things that have these difficult operations, they really, they lead to, if you had a better infrastructure, you could run them more efficiently. There were some very serious challenges that Twitter had to get through when it came to needing this new infrastructure. Just a couple real quick, deployment and scheduling for fault tolerance. The first version of this at Twitter was an Excel spreadsheet where the columns represented the racks and the rows had, were actually the services running on each of those machines in the racks. Scheduling for elasticity and efficiency, like forget about it, right? No one's going to think about, I've got this cool Excel spreadsheet. I'm going to go and I'm going to add a couple more instances of a service to a couple of these spots because they need more resources. It just wasn't happening. There's a lot of other challenges that actually had to occur. I kind of wanted to capture, in a bunch of my slides, I like to capture some real emails from Twitter in the early days. So the date is accurate. The names are all changed except for Abdur, who was my boss. He was the chief scientist there. And so this says, FYI, this machine had to be rebooted. Were there any production services running on this machine? Right? So like this was scheduled. This was state-of-the-art scheduling at Twitter in the early days. And then this one, which is maintenance, I like to call maintenance planned failures. Because when you do maintenance, you're basically inducing a failure in the system. You just know when you're going to do it. And so this is people asking like, hey, we'd like to run this stuff. At the bottom, preferably they are on different rack switches and power feeds so that they are fully redundant. Because if you wanted to do maintenance, you'd actually want that full redundancy. So the story here was really that all these organizations were basically doing static partitioning, Twitter being one of them. And could they actually transition from this static partitioning world to a world in which we could run something like an Apache Mesos in between the applications instead? And so that's really what is kind of, to me, the biggest thing that's really surging this interest. And a lot of people, when I say that to them, I say, yeah, we kind of want to run this thing in between the other stuff. They said, isn't that what we tried to do with hypervisors? And wasn't that the whole point of virtual machines? And like, why is this somehow new and different and what's happening? And I think what's really interesting to me to capture that is this picture, which is the siloed static world was kind of mainframe. We ran single applications. Then we broke it up into a whole bunch of different physical machines. We moved to this virtual machine world, and we had things like virtual machine schedulers and all that stuff. And now we're getting to more of this unified world. So why are these two so different? And really, to me, the better question is why are these two so similar? Because from developers' perspectives, when they moved from the physical world to the virtual machine world, nothing changed. Previously, if you wanted to run your application, you were given a machine as an interface. Once you got virtual machines, if you wanted to run your application, you were given a machine as an interface. And now operators were definitely more easily provisioning you those machines, but developers didn't have anything that was making their lives much, much easier. And DevOps came out of that. And like, what's going to make it easier for developers to do operations because the machine is actually the interface. And really, to me, this next big step is because we stopped thinking about machines. And when developers want to run applications, they're just launching applications. They're not thinking about machines. They're not getting machines as interfaces. They're just resources and the apps they actually want to run. And that's why we really think about the data center as being like one big computer that just has a bunch of machines where you want to figure out where you're going to run those applications. These are now my kind of company pitch slides, so you can ignore the pitchiness. But the data center computer really needs something like an operating system. If we're going to think about all these as just a big pool of resources, and you have the data center computer, and you just want to run your applications, you should have something like a data center operating system. And that's what we're doing at Mesos here. We're at the core of the data center operating system is Mesos. It's kind of the distributed systems kernel that's providing a bunch of the primitives that I talked about in a previous slide, doing the two-level scheduling. And we're building a lot of the pieces around Mesos. So you can really think of it more as a microkernel-like operating system model. There's a whole bunch of other components that are really critical for running your applications that don't live in Mesos, but they really exist there. And then, and again, this is kind of the analogy here. In the single host operating system space, there's things like Red Hat and Ubuntu and CentOS. And for us, we've built what we call the DCOS, which is our distribution, if you will, of a data center operating system with a lot of those components, and then Mesos at the core. And our goal is really to enable running all these different kinds of workloads, not just microservices and containers, but also big data, analytics, storage, things that are typically solved today as these distributed systems that I started this entire talk all about, which are actually really, really hard to run. But now the big advantage of to have something like the DCOS and Mesos is you can run these things far more effectively. So we have what we call control planes for Kafka and Cassandra and Spark and HDFS that run natively on top of Mesos and the DCOS that literally makes operating these things far easier than if you were to do all this stuff yourself. And the idea is that you don't need the book anymore because you can encapsulate everything you would have done in the book in software that's actually using the interface and the underlying infrastructure. So the joke I sometimes like to make is that Mesosphere is disrupting O'Reilly, which is the guys that make the books. Okay, so here's just an example of some of those distributed systems that we've actually made run. And a big goal of ours is you could build a distributed system in one organization, and if you built it on top of Mesos and the DCOS, you could just deploy it in another organization. It'd be as easy as building an application on top of Linux and running it from CentOS to Ubuntu or to Debian or anything else. You can check it out at dcos.io. And then I thought I'd end with a joke. Most of my time these days, I think about this quote a lot, but with some slight variations. Instead of levels of abstraction, it's managers. Mechanisms that exist that facilitate the exchange of information between levels of managers is a good thing. And managers exist for good reasons, but without sufficient communication, they force suboptimal outcomes. This is pretty much my job now. So anyway, thanks so much for having me. Take any questions?
So about RDF, the dominant resource, if I understand correctly, you want to take dominant resource and go down the allocation of it to a task, or whatever you call it, such that it becomes about, in other words, you want to give the task as little of the resource as necessary, right? Saying it's enough to give it 1/10, because giving more would not make it up fast.
Yeah, I mean, it's really targeted at saying, if we've given you these resources statically, that's the best you would have done. And so it's about being able to say, we're going to make sure that you're going to do as well in a non-statically partitioned cluster as if we would have given those resources to you statically. But now, because it is one single cluster and I'm running multiple applications on the same resources, I can pack in other tasks from other partitions in that extra free space.
I see. So there seems to be a relationship to other bottlenecks on which this task is stalled or slowed down, right?
Oh, yeah.
In a sense, you would like to assign as much CPU and as much memory so that both the CPU and memory are, so to speak, the same bottleneck for a given.
Yeah, I mean, I think one of the things that's pretty interesting is that there are a lot of tasks that get run. There's a lot of tasks that are very dynamic, very life-esque dynamic, where they're constantly changing the amount of resources. Or at least if you gave them a container of resources, they might constantly change, but they can kind of live in that one container. And so what most organizations are doing is they're picking some allocation that they believe is the best for now for that application, and then they're plopping out many instances of it. And so really, we focused on the single dominant resource. But work that we're now doing at Mesos here, as we're running into issues of certain ways that this you see this in the cluster, is and I think this is why I'm addressing the question this way, is it's more like a dominant resource of a template of resources. It's like you almost want to think about your dominant resources being 3 CPUs and 2 gigs of RAM versus just CPU. Because then you can start to do more interesting things when it comes to scheduling in the cluster. And in fact, like the other reason why you do that is because scarce resources does not work well in a DRF model. Because if you use most of the scarce resources, you're using a lot of your dominant resources, right? So there are a bunch of changes that we're trying to introduce that are very much in this realm of don't just make it for a single resource, but make it actually for like a package of resources or a collection of resources.
Let's talk more.
Okay, sounds great.
A question on the PG slide, why isn't there a phone on that scale? Why does it end with a desktop on the...
Oh yeah, there's totally a phone. Yeah, there's totally a phone. There's a version of this talk where there's a phone and we say, the phone is exactly another place where there's an operating system and you want applications to just use that operating system.
Yep. How do you upgrade the Mesos layer?
Great question. Yeah, that's a really good question, right? So if we're going to be the thing that makes it easier for distributed systems to operate, we better be something ourselves as a distributed system that can easily be operated and upgraded. That's how I reinterpret your question.
Yeah, great. Yeah, so it's some kind of bootstrapping problem, right?
Yes. So we've put a ton of time and effort into that. One of the reasons why the system is literally just masters and agents is so it's very simple. And to upgrade Mesos itself, we've actually put a ton of time and effort into making it so that every single next version is backwards compatible with the previous version. And every single task or job or anything that we run, we will not terminate when we upgrade. So we'll keep everything running, and then when you relaunch us, we find everything. So I didn't get into the details of exactly how this works, but Mesos runs on top of Linux. Meso is like middle OS, right? It's like there's still the host operating system, and then there's Mesos on top, and then the applications on top of that. So as long as Linux is running, you can just stop our process. Any of the processes we launched will keep running. We'll bring our process back up, and then we can again monitor and watch and kill and launch more things and whatever else we want to do. So, but yeah, and that's pretty critical. Before we had some of this functionality in Mesos, for some of the larger clusters at Twitter, it took weeks to do an upgrade of Mesos because you'd induce a failure on that box to do the upgrade, and all the tasks would get rescheduled someplace else. And then you'd go induce a failure on that box, and if you weren't lucky, everything got scheduled in the same box, and you just watch these tasks bounce between the cluster. And so we had to do it, we had to build this thing in so that we could upgrade it really easy, and then we could huge swaths of the cluster in minutes and not kill anything. And we still wouldn't do everything at the same time because we probably have a bug somewhere.
So you have Kafka and Cassandra listed as coordinators on there. Yep. And things like that seem like they have really long-lived state that needs to be maintained in your system. So do you kind of keep that state localized within the container or the host, or?
So that's a great question. So there's two parts of the state that those systems have. There's the actual persistent state, like in Kafka, the stuff that's in the message queues, in Cassandra, the stuff that's in that are key values. That stuff is written to the local disk on the machines, and the new primitives that we've introduced for that to the Kafka and the Cassandra coordinators are what we call persistent volumes. So in the same way that on Linux, when you're like, oh, I want to save some stuff, my primitive is I open a file, and then I read and write to the file, we have a primitive which is we'll give you a persistent volume, and then you can read and write to that persistent volume, in which you're writing that to those files. And then you can get that back, we track it for you, you have a reservation for that, so that's the thing that we basically introduced for the Kafka and Cassandra state.
That affects your scheduling as well in your...
So it most definitely does. It most definitely does. So a great example of that is in certain circumstances, you might want to do maintenance on a machine where the machine is going to be out of commission for a long period of time. If what got scheduled on that box was a Kafka or Cassandra using a persistent volume, in the old ways, the static partition, you'd like go to the Kafka and Cassandra team and you'd be like, hey, I got to pull this machine out, copy your data, figure out what you need to do. In the new way, there's another upcall, and that upcall is called in Mesos, and that upcall is called an unavailability. And so we say to the Kafka and the Cassandra coordinators, these resources are going to be unavailable at this point in time. And then they have some amount of time to figure out what they want to do, and they can acknowledge or they can negatively acknowledge. We put that in because some coordinators are going to want to let their Kafkas negatively acknowledge, and they're still going to come in and do the old style way. But otherwise, they can just use that time to get resources from another place, copy their data over themselves, get the persistent volume there, get it off of the previous box, the machine's been drained, and then you can go from there. And we specifically introduced this as an unavailability versus like a maintenance because we can also use it for other things. When we want to defragment the cluster, if we want to like turn off a particular machine, we're not doing maintenance there, but we could move jobs around by saying, hey, these resources are becoming unavailable now, you got to get off. The other one that we haven't used it for yet, but people want to use it for is refragment the cluster. So if too much stuff lands on one box and the current Linux isolation mechanisms are not working well, you might want to move something off and say, hey, I need you to get off this box in the next little bit, and then go from there. So that's a really great example of the two-level, the upcall mechanism being introduced to do something that otherwise previously would have been an absolute pain in the butt to do from an operator perspective. And then the other part of your question was the other storage that a Kafka or Cassandra coordinator might have is just knowing where they're running all their things and what they're trying to do. And that's not part of us. That's just something that they would store themselves.
Yeah. So why don't we pause there? If people have more questions or questions they don't want on camera, they can come up. I probably should have mentioned at the top why Ben is here today, which is tonight he's getting the College of Engineering's Early Career Diamond Award, which is a pretty darn neat thing. And in a long line of, even in this talk, you mentioned Memcached, which comes from a UW alum, and MapReduce, which comes from a UW alum, and now we have Mesos, co-created by a UW alum. So thanks.
And at least Fitzpatrick won this award.
Yeah. Yeah.